Okay. Yeah, so thanks to the organizers for putting on this seminar. Today I'll be talking about some joint work with my advisor, Sourav Chatterjee, on a state space for the 3D Yang-Mills measure. And so I'll try to give a general sense of what we did in this talk, but I won't be able to give any precise statements. Yeah, so let me start by giving some background. So Yang-Mills theories are supposed to be the mathematics behind the standard model of particle physics. And the standard model of physics describes the behavior of elementary particles at very short distances. And so even though we don't currently have a rigorous understanding of these theories, physicists nevertheless have been able to use them to make very, very, very accurate physical predictions. And so there's no question that the standard model actually does describe nature. But there is this mathematical question of how we actually understand these things. And so to draw an analogy with a more familiar object, Brownian motion, it's sort of, well, I mean, even before Brownian motion was rigorously constructed, physicists were still able to use or to model, say, the motion of molecules by Brownian motion. And then using this model, they were able to make physical predictions, which were then experimentally verified. All right, and so to do this, we didn't actually need, or physicists didn't actually need a rigorous construction of Wiener measure, right? But mathematically, well, maybe we want to have a rigorous construction because now we know Brownian motion is a very rich mathematical object that's at the starting point of many different fields. And so the hope is, or the expectation is, the same is true for Yang-Mills theories. And so the first step towards a rigorous understanding would be to actually construct a four-dimensional Yang-Mills theory. And it's 4 dimensions because space-time is 4-dimensional. Okay, but for now, 4 dimensions, it's still too hard. So today I'll just be talking about some progress towards constructing a 3-dimensional Yang-Mills theory. So 3 dimensions is a bit more tractable and also it hasn't been done yet. I'll say a bit more about this later, but the only dimension where we where we actually have a rigorous construction is 2 dimensions. Okay, so what do I really mean when I say construct a Yang-Mills theory? So usually what we mean by that is we want to construct a certain probability measure called the Yang-Mills measure on a space of connections on a principal bundle. Okay, so these notions of connections and principal bundle, they're things coming from geometry. But for this talk, I'm just going to make the geometry as trivial as possible. So as we'll see later, these connections are really just functions. So really, we want to construct a certain measure on a space of functions, or we want to construct a random function, or actually a random generalized function. So it'll be a distribution. Okay, so associated to the Yang-Mills measure is a certain parameter G called a structure group. So G is supposed to be a closed subgroup of the n by n, or the group of n by n unitary matrices for some n. So G is a Lie group, and because it's a Lie group, it has a Lie algebra. So let's let frac G be the Lie algebra of our structure group. And okay, so in this talk, we basically don't need to know anything about Lie groups and Lie algebras, but one thing I will say is that, okay, so the Lie algebra is again some collection of n by n matrices. Moreover, it has the structure of a vector space. So actually, it has the structure of a real finite dimensional inner product space if you equip it with this Frobenius inner product. So for us, that's basically the main thing we need to know about the algebra. It's basically some vector space like R to the K or something. Just think of it like that. And then okay, now I can define what a connection is. So let's let D be at least 2. So for the purposes of definitions, I can work in any dimension for now. So connection for us will just be a function from the underlying space. So for us, it'll be the D torus to G to the D. Or in other words, so basically a connection is a D tuple of functions where each component function maps into the Lie algebra. And so here I'm taking the base space to be the torus for mathematical convenience because it's compact and boundaryless. So that'll be useful. Okay, so now, so given a connection, we can define this thing called the curvature of a connection, which is this matrix of functions. And so the ijth component function of the curvature is defined as partial iaj minus partial jai plus the commutator of aiaj. And so as usual, this is the matrix commutator, so aiaj minus ajai. And so one thing I should note is that the commutator of 2 Lie algebra elements is again a Lie algebra element. And so for that reason, each of these component functions maps into the Lie algebra. And so yeah, to reiterate, the curvature of a connection is just this matrix of component functions, each mapping into the Lie algebra. So now that I've defined the curvature, I can finally define this thing called the Yang-Mills action. of a connection, and it's simply just the squared L2 norm of the curvature, or in other words, the sum of the square L2 norms of each of the component functions. So you can think of this Yang-Mills action as a nonlinear version of the energy of the connection A. And so the d-dimensional Yang-Mills measure is this formal probability measure given by this expression here, which is basically a normalizing constant times e to the minus Yang-Mills action of A, dA. So this dA is formally the Lebesgue measure on the space of connections. So what we mean when we say we want to construct the Yang-Mills measure, well, we want to give we want to give rigorous mathematical meaning to this formal expression. And so to draw an analogy again with some more familiar objects, recall Brownian motion, whose law can be written as this formal probability measure. So the density will be e to the minus integral 0, 1 f prime squared. And so basically we note this thing is basically the Dirichlet energy of f. And so more generally, the d-dimensional Gaussian free field has law which is formally given by, again, it's e to the minus integral Dirichlet energy of f, or e to the minus Dirichlet energy of f. And so just as we have been able to successfully give rigorous meaning to these latter two formal objects, the goal is to give rigorous meaning to this first formal object. And so if we do so, that means we would have constructed the Yang-Mills measure. And so now let me quickly survey some previous work in this area. So as I mentioned before, 2 dimensions is by now very well understood due to many, many works. And so here I'm just giving an incomplete list, but yeah, let me single out some specific works. So Levy in 2003 and 2010 succeeded in constructing the Yang-Mills measure as a stochastic process of observables. And then following up on that, Chevyrev in 2019 constructed a random connection whose observables match with Levy's construction. So it's a random connection which is consistent with this prior work. And then in 2020, this group, Chandra, Chevyrev, Heyer, and Shen, or Chandra et al., they mathematically initiated this stochastic quantization approach to constructing a Yang-Mills measure. So they constructed this Markov process on a state space, and as far as we can tell, it's still conjectured that this process should have a unique invariant measure. If this conjecture is proven, then they would basically define the Yang-Mills measure as this unique invariant measure. So that's the work in 2D. And as I mentioned earlier, 3 dimensions and 4 dimensions is less well understood. So of course there are works working in 3 and 4D, but as far as we can tell, there is no construction of the 3 or 4D Yang-Mills measure as was done by, say, Levy or Chevyrev. Right. But I should mention that Chandra et al. Do mention in their 2020 paper that they have a forthcoming work in 3 dimensions, and so I'll be very interested in seeing what they do there. Okay, so before moving on, let's go back to this previous slide and think, well, okay, so what's one general approach for giving mathematical meaning to these types of formal expressions? Well, so one general approach is we first take a sequence of rigorously defined finite dimensional approximations. So for Yang-Mills theories, these approximations would be, for instance, lattice gauge theories. So in this talk, I won't define lattice gauge theories, but just know that they're basically obtained if you discretize the underlying space. For us, it's a torus by a lattice. So basically, these lattice gauge theories are statistical mechanical models on a finite lattice. So think of it as like an Ising model. And so we know Ising models on finite lattices are well defined. So there's no problem there. Okay, so these things are mathematically well defined. And then we would basically want to take a scaling limit. We send the lattice size or the lattice spacing to 0, and we would want to show that these approximations converge as probability measures on some appropriate state space. Right? So that's this general approach. If we can make this work, then we can give rigorous meaning to those formal probability measures. So to draw an analogy, coming back again to Brownian motion, well, the approximations, for instance, would be random walks. The state space would be C01, and convergence would be shown by showing tightness plus convergence of finite dimensional distributions, right? Because tightness gives subsequential limits, and then convergence of the FDDs shows that the subsequential limits are unique, and so we get actual convergence of the original sequence. And so in analogy, we would want to make this type of approach work for Yang-Mills, and so that's what this work with Sourav. This is what we do in this work. So first off, I should say for Brownian motion, the state space C01 is kind of clear, I guess, from the start, but for Yang-Mills, it's much less clear what the state space should actually be. And so the first thing we do in our work is we propose a state space, or we define a state space, which is inspired by this previous work of Charalambous and Gross in 2013. And then we give a tightness criterion for probability measures on this state space. So basically we say if a certain criterion is met, then we would be able to obtain subsequential limits. And once we have subsequential limits, we could define the Yang-Mills measure as one of these subsequential limits. And of course, to show uniqueness, we would need to show convergence of FDDs, but that's sort of a separate problem. And moreover, we make some progress towards verifying this tightness criterion. So specifically what we show, and okay, so this is sort of a hand-wavy statement. We give a mathematical formulation in the paper. But for this talk, let me just say, so basically if we show that if the Yang-Mills measure has this certain property, it has this similar short distance behavior as the three-dimensional Gaussian free field. In other words, it has similar regularity as the 3D GFF. And so this property is expected. For example, Chevy-Rev in his 2019 paper mentioned that it's expected in 2 and 3 dimensions. So assuming this holds, then we have tightness. And so basically what's left to show the existence of subsequential limits of approximations would be to show that this expected property holds. And to go more into detail about this property, we basically assume that the 2-point function of this Yang-Mills measure blows up at most distance to the -1. And so recall the Gaussian free field, the 2-point function of the Gaussian free field is the Green's function. In 2 dimensions, or in 3 dimensions, the Green's function blows up by -1, or distance to the -1. So we're basically saying, okay, assume that the 2-point function of the Yang-Mills measure is only as singular as the 2-point function of the GFF. Then we have tightness. Then we have some subsequential limit. This is sort of like the hand-wavy statement. And of course, I'm sort of, to be totally transparent, we're also assuming some technical conditions that are needed in the proof. But showing them on the other hand might be kind of hard. And so yeah, finally, as I mentioned earlier, convergence of finite dimensional distributions is sort of a separate problem completely. Here in this work, we're just worried about tightness. So tightness, if we are able to carry this through, we would get subsequential limits. But to show, say, uniqueness of the subsequential limit, we would need to have convergence of FDDs, which we have nothing to say about that at the moment. Yeah, so that's it. Thanks for listening.